one considered. Yeah. Slavery? No, it's not.
Right, so yesterday we were talking about the three types of discontinuities, right? So what were they? A whole or removable, a jump, and yeah. So you just need to know those three terms and how to identify them graphically. That's it. That was the whole deal yesterday. Okay, today we're going to talk about continuity of piecewise functions. So we kind of have all the parts of this. We just have to put it all together in one problem, right? So they're going to ask you for a particular piecewise function, is this a continuous function or not? That's the bottom line, right? So, for example, suppose they said something like f of x equals piecewise function 2x minus 4 if x is less than 2, and negative x plus 2 if x is greater than or equal to 2. So they'll give you a piecewise function like this. And they'll say, is f of x continuous at x equals 2? That's the question. Well, remember, there's three things that have to be true in order for this function to be continuous at x equals 2. The first thing that has to be true is that does f of 2 exist? Like, is it defined? And all you need to do to confirm that is just make sure that it appears somewhere over here in the intervals where the function is defined. As long as 2 appears somewhere over here, then f of 2 exists, right? So you just say yes, since 2 is in interval right there. Since 2 is in that interval, that means that f of 2 is defined. It exists. The second thing that has to be true is that the limit has to exist. So does the limit as x goes to 2 of f of x exist? And for this, you just have to think back about how to calculate limits of piecewise functions. How do you do that? Do you remember? Exactly. You just take 2, you plug it in here, and you take 2, and you plug it in there, and make sure you get the same thing. And remember, the theory behind that is you're really just calculating the limit as x goes to 2 from the left, and the limit as x goes to 2 from the right. Right? So if you're calculating the limit as x goes to 2 from the left, you're looking at the top part of the function, because that's what the function is, to the left of 2. So if you substitute that in, you get 2 times 2 minus 4, which is 0. If you calculate the limit as x goes to 2 from the right, then you plug it into the bottom part, because that's what the function is to the right of 2. So you get negative 2 plus 2, which is 0. Since these match up, you can then say, yes, the limit as x goes to 2 of f of x equals 0. And then the last question that you have to answer is, does the limit as x goes to 2 of f of x equal f of 2? And the answer is, yeah, it does, because I found the limit, it's 0. And to figure out what f of 2 is, I just need to substitute 2 in there, but that's how I got the limit, right? I substituted 2 into there and got 0. So yeah, this is definitely true. 0 equals 0. So the answer is yes to that question. So since all three criteria are met for the function to be continuous, you could say yes, the function is continuous at x equals 2. So yes, f of x is continuous at x equals 2. Now we can kind of streamline this process a little bit. You don't have to go through all this ridiculousness. You could just say, if we can figure out that the limit exists, then just by the way that we calculate limits of piecewise functions, then you can say that this part's true. So really all you need to do is make sure that the limit exists. In other words, make sure that you get the same thing when you plug it into both pieces. And make sure that the x value in question is actually in the interval. As long as those two things are true, you're good. It's a continuous function. Okay? Let's do a couple other examples. So suppose I have something like this. What if I have f of x equals 2 pieces, 13 minus 4x squared, if x is less than or equal to -3, and -20 plus x if x is greater than -3. Okay? And the question is f of x continuous at x equals -3? So again, all I'm going to do, the shortcut is, make sure -3 is over here. It is. It's included in that interval. So that's the first part of it. The second part is substitute -3 into both pieces and make sure you get the same thing. So the question is 13 minus 4 times -3 squared. Does that equal -20 minus 3? That's the question. You just want to verify if that is true or not. If this isn't true, then the answer is no, it's not continuous because the limit doesn't exist, right? So I have 13 minus 4, 13 minus 4 times 9. That's 13 minus 36, right? Which is -23. And here I get -23. So the answer is, yep, definitely true, right? Because all three criteria are met. The function is defined at -3. The limit exists, and f of -3 is actually -23. That's how I got this number right on this side, is I substituted -3 in there. So I'm not skipping steps. I'm just realizing that I don't need to be redundant and do it twice. Okay? How about this one? What if I have something like f of x equals -2x plus 3 if x is less than 1, and x squared if x is greater than 1. Is f of x continuous at x equals 1? Why not?
Because it cannot equal 1 according, it's in neither of those.
Yeah, because it's not defined at 1. 1 is not included in either one of these intervals, so you can say right away without any questions about it, the answer is no. Since f of 1 is undefined. Because 1 is not included in the interval. What if they gave us this same piecewise function and they said, is f of x continuous at x equals 0? What about that?
Yes.
Absolutely, yes. I don't have to do any further work because around 0, we're talking about this function right here, which is just a polynomial. This is just a line. It's definitely continuous at 0. It's just a line. So the answer would be yes. This isn't even the interesting part of the piecewise function. So yes, between the interesting parts, which are the parts where the the function might change, the function's definitely continuous, right? Does that make sense? So those are two tricks they might try and pull on you. They might give you, ask you about the point where the function changes, but yet the function is undefined at that point. That's one trick. And the second trick is they might ask you something about a point that's not even where the function changes. In that case, the answer is yes all the time. Okay? Let's see if I can. How about this one? What about f of x equals x squared minus 1 over x minus 1 if x does not equal 1 and 2 if x doesn't equal 1. All right, so this one's a little bit different because the intervals in which the pieces are defined aren't necessarily like everything to the left of this number and everything to the right of that number. Instead, it's like everything except a number and then at that number. So this one's a little bit different, right? So same question, is f of x continuous at x equals 1? Well, we still need to ask the same three questions. Is it defined at 1? Yes, it's 2. So that part is checked off. Really, all we need to check now is the limit as x goes to 1 equal to 2? If the answer to that question is yes, then the answer to this question is yes. And if the answer to that question is no, then the answer to this question is no. Does that make sense? So the real question here, is the limit as x goes to 1 of f of x equal to 2? That's the real question. Does everybody see how answering this question is really answering this question?
Yeah.
All right, so how do we calculate the limit as x goes to 1?
Factor x minus 1 into x plus 1 x minus 1, then cancel out the x minus 1s, and then you get 2.
Right, exactly. Okay, so the first thing to realize is that if you're close to 1, then the function is actually this function. We don't care about what's happening at 1. When we're looking at the limit as x goes to 1, we don't care about what happens at that point. We only care about what happens near that point. So we're talking about this function, x squared minus 1 over x minus 1. So now we're like back in time 4 weeks, and we're calculating limits of rational functions. The first thing you do is you try and plug in the number. That doesn't work. What's the second thing you're supposed to try and do? Factor. And this factors. X minus 1, x plus 1 over x minus 1. Those cancel. And then you can try and substitute the number in again, and this time it works. You get 2. So think of the 3 things that have to be true for the function to be continuous. The function has to be defined. It is. It's 2, right? Right there. The limit has to exist. It does. It's 2. And those 2 things have to be equal. And they are. 2 equals 2. So this answer is yes. It is continuous at x equals 1. Because all 3 criteria for continuity are met at that point. All right, let's just do one more example. How about f of x equals, let's say the pieces are square root of x plus 1 if x is less than or equal to 3, and 5 minus x if x is greater than 3. Is f of x continuous at x equals 3? So you check to make sure 3 is here. It is, right there. And then you find the limit. So you substitute 3 in here, you get the square root of 4. Substitute 3 in here, you get 2. And that's definitely true. So the answer here would be yes. The limit exists, function's defined, and those 2 things are equal to each other. Everybody understand? Okay, so on Delta Math, the assignment's just called continuity of piecewise functions. Okay? That's it. Oh, tomorrow, before I forget, tomorrow there's no quiz and there's no lesson. It's just going to be a free day, and I'm actually not going to be here. There'll be a sub here, but just bring like some work to do, or you can sit here and talk. I don't really care. And that's it. That's the whole plan for the day.
Laura, when you get to that question, just like,